Hi everyone, welcome back to Chapter 2 Thermochemistry. In this chapter, we are going to talk about Chapter 2.4 BORN-HABER cycle. So by the end of the lesson, you should be able to define lattice energy and electron affinity. Explain the following effect to the magnitude of lattice energy. Ionic charges, ionic radii. Construct the BORN-HABER cycle for simple ionic solid using energy cycle diagram and energy level diagram. Then, calculate the enthalpy changes using BORN-HABER cycle. So for this subtopic, we also have a few definitions that you need to understand and memorize and for the use to construct a thermochemical equation. So first of all, we have lattice energy. So this lattice energy, you can use the symbol either is enthalpy of lattice or lattice energy LE. So for lattice energy, we have two definitions. First of all, it refers to energy release when one mole of ionic solid compounds form from its gaseous ion. So lattice energy will involve the conversions between gaseous ion and the solid compound. Okay, so heat release, it means that it is bond formations. So from gas into solid phase. Okay, so bond formations release energy. So giving you the examples over here, energy release when one mole of the solid ionic compound, sodium chloride, is formed from its gaseous ion. The second definition for lattice energy refers to the energy required when one mole of ionic solid compound is separated completely into its gaseous ion. So energy required for bond breaking process. So from solid into gas. So very important that you take notes on the phases. So in this case, the energy required, okay, when one mole of the solid ionic compound is broken down, okay, is separated into its gaseous ion. So energy release, we're focusing on the product, okay, the solid ionic compound. Energy required, we're focusing on the reactant. So keep this focus as one mole according to the definitions. Next definitions, we look into ionization's energy, IE. So this one is revisions for you. So ionization's energy refer to the minimum energy required to remove one mole of electron from one mole of gaseous atoms or ion. All right. So minimum energy required, that means it will have a positive sign for its energy. So it is energy required to remove one mole of electron from one mole of gaseous atom. The second equation, energy required to remove one mole of electron from one mole of gaseous ion. All right, so this is a revision. So I hope everyone know how to write the equations for IE. Alright, so next one we have this electron affinity. Please do a corrections in the notes. This is a typing error, affinity, and it represent by the symbol EA. It is directly opposite with the IE. Alright, so for this electron affinity, it refers to the energy change when one mole of gaseous atom gain one mole of electrons to form an ion. All right, so in this case, energy change refer to it can be positive or negative. So energy release, for the first one, energy release, when one mole of gaseous atom gains one mole of electrons to form an ion. So our focus will be one mole of gaseous atom, the reactants here. Okay, and the second EA2, the energy required, okay, for one mole of the gaseous to get one mole of electrons to form an ion. So it will do it step by step. EA1, we gain one mole of electron. EA2, we get the second mole of electron. So similar like our ionization's energy. Remove electron one by one. For EA, you gain electron one by one. Alright, so the last definitions you have here, this one is an additions for you. It refers to bond energy, BE. It is the energy required to break 1 mole of molecule into its individual atom. So this bond energy is quite similar to atomizations. But for atomizations, we focus on the product when gaseous atom is formed. For this bond energy, we focus on the molecule that we are going to break. Okay, so when 1 mole of the molecule is break into its individual gaseous atom. Okay, so energy required. So in this case, we focus on the reactant. Okay, we focus on the reactant. So keep this Cl2 as 1 mole. Again, this one is gaseous atom. There is no charge for this one. So from Cl2, we will form 2 Cl atom, gaseous molecule into gaseous atom. Alright, so next we want to look at the factors that affect your magnitude or strength of lattice energy. Again, recall that lattice energy involves the conversions between gaseous ion and solid ionic compound. So between gas and solid or solid with gas. So the first factors, it depends on the ionic charges. So when the ionic charges increases, the forces of attractions between ion become stronger. So this ion refers to the cation and anion, and therefore lattice energy increases. Or we can also say that the lattice energy become larger, or in brackets over here, the lattice energy becomes more negative or more exothermic. It means that it releases more energy. Radii. So when ionic radii decrease, the forces of attraction between two of these ions become stronger. That means they are getting closer together, so the forces of attractions become stronger. And therefore, lattice energy becomes larger, become more negative, more exothermic for the bond formations process. The relationship between our lattice energy with ionic charge with ionic size. This ionic size is the same as ionic radii, ionic radius. Okay, and if your ionic charge increases, lattice energy increases. If your ionic size decreases, lattice energy increases. So look at the relationship. The charges increases, lattice energy increases. If the size decreases, both of the ion getting closer, therefore you will have a bigger lattice energy. So for the first example here given you have your magnesium fluoride ionic compound, magnesium oxide ionic compound. So based on their lattice energy, we have a negative sign. So this negative sign refer to bond formations, which is from gaseous into solid. All right, so this is bond formation. Remember, yep, negative sign, release energy. So comparing the ion exists in the ionic compound here, we have Mg2 plus, similar for both. And then we have F minus and O2 minus, O2 minus. So if the charges is different, we will compare the charges first. So the ionic charge of the oxide ion is greater than the fluoride ion. O2 minus is greater than F minus. Therefore, the electrostatic forces between Mg2 plus and O2 minus is stronger than that of between the magnesium ion and the fluoride ion. Okay, you need to mention about the electrostatic forces between cation and anion in that compound. And finally, to conclude that lattice energy for magnesium oxide is greater than magnesium fluoride. So this is the example where we compare the ionic charge. Bigger the charge, bigger the lattice energy. The next example. So the second example here gives you lithium fluoride, sodium fluoride. All right, and the lattice energy, again, negative sign refer to bond formation, so from gas into solid. And as we can see over here, lithium fluoride has a more negative lattice energy or bigger lattice energy. Okay, so looking at the ion, fluoride ions are the same for both, but in this case, lithium it exists as Li plus and A plus. This one is a positive, yeah. So both of them have the same charges, then we have to compare about the size. Remember, priority goes to ionic charges first. If they are the same, then only we compare the ionic size or ionic radii. So the ionic size of lithium Li plus is smaller than Na plus. As we know that going down the group, the size increases. So Li sit on top of sodium in periodic table. Therefore, Li plus is smaller. Therefore, the electrostatic forces between Li plus and F minus is stronger than that of sodium ion and fluoride ion. And we make a conclusion. Lattice energy of LiF is bigger than NAF. So we make a conclusion that lattice energy of lithium fluoride is bigger than the sodium fluoride.